Okay, we're going to continue on with 11.02 with writing acid-base reactions with water. In other words, the hydrolysis. What happens when we drop an acid or a base into mod water? Way back in Module 4, you learned to write molecular equations and net ionic equations. Net ionic equations only show what is going on with the ions or the molecules. Any spectator ions are omitted. So remember what we did with these is we omit spectator ions. Spectator ions are ions that do not participate in the reaction. They're just spectators. The other thing I want to look at is having you use single or double arrows as appropriate for strong and weak acids and bases. So I've got some examples for you here. First, we have HCl reacting with water. That is a strong acid. So we're going to make hydronium ion and chloride ion. And so our final equation is going to be H plus H2O makes H3O plus because the chloride ion is a spectator ion. So it ends up being crossed out. Our next one is hydrofluoric acid. Because that is a weak acid, we are going to use the arrow showing that the reaction is going significantly forward and in reverse. In this case, HF stays a molecule because it is a weak acid. So remember, weak acids stay in the molecular form. In net ionic equations. So in this case, our net ionic equation would be the molecule HF plus H2O being in equilibrium with the hydronium ion and fluoride ion. And then the last one I have is ammonia reacting with H2O to form the ammonium ion and OH minus. In this case, the molecular equation is exactly the same as the net ionic equation. I just noticed there I've got an F minus missing there, so let's go ahead and put that in. Okay, so I'm going to work through some examples for you, and you also should be able to predict the reaction. So we did this also back in Module 4. So HNO3 plus H2O, we are going to generate in one way because HNO3 is a strong acid, the hydronium ion plus NO3 minus. Now, remember that because this is a strong acid, it is going to dissociate into H plus NO3 minus. So now I'm writing everything out. This is my ionic equation here. And this is going 100% to H3O plus NO3 minus. In this way, we can see that the nitrate ions will be omitted. They are spectators. So our net equation, our net ionic equation is H plus H2O is going to form the hydronium ion. And I'm going to go ahead and try to put a tidy circle around that so you can see that that's the net ionic equation. The next reaction that we are looking at is a carboxylic acid. Remember that this is our labile, our reactive hydrogen. Since it's a weak acid, we have to make sure that we use arrows going forwards and backwards, showing it's in equilibrium. We're going to be forming H3O plus CH3 CO2 minus. We look to see if we're going to write an ionic equation, but this does not. We're going to keep this as a molecule. So keep as a molecule, which means that our net ionic and our molecular equation end up being exactly the same thing. So we have CH3 CO2H because we keep it as a molecule plus H2O is in equilibrium with the hydronium ion plus the acetate ion. Now, I also want to draw to your attention that these reactions must be balanced for charge as well. So when I look at this, I double check and I go, oh yeah, I got a plus there, I got a minus, that is neutral, and my reactant side as written is also neutral. Okay, so I am going to pause here and you are going to try to do the next two. Okay, so take a look at the answer that I have displayed and see how you did. First thing is you should have realized that nitrous acid is a weak acid, so you have to have that arrow going both ways. Nitrous acid is going to stay a molecule, so our original equation ends up being the same as the net ionic equation. So let me go ahead and label this as the net ionic. Our next one is perchloric acid. That's one of your strong acids. So you need to show a one-way arrow showing that you're going to be forming the hydronium ion and the perchlorate ion. We can cross out the perchlorate ions on both sides, so we end up with this as the net ionic equation. So I've shown you acids being dropped into water. Now we're going to take a look at a nitrogenous base. So we have here, there's going to be a lone pair up here. So that means that this nitrogen can accept a proton from water. This is a weak base. I need a two-sided arrow. So let's go ahead and put in the two-sided arrow. The amine is going to be picking up a base. So I'm going to have NH2. Remember, you've got to make the conjugate acid. This now has a positive charge. And then I'm going to be producing hydroxide ion. So let's take a look here and whether I'm balanced for charges on both sides. I have a plus and a minus, which is neutral, and the reactant side is also neutral. Let me off to the side here. Anytime you've got 4 bonds leading to a nitrogen, you are going to have a positive charge. So this is something that tends to confuse students. If you pick up a hydrogen as you go from the amine to the ammonium ion, then you've also got to pick up that positive charge. All right, let's take a look at our net ionic equation. In this case, there is nothing that is going to ionize. This stays a molecule. So in this case, the molecular and the ionic equation are the same. So the molecular and net ionic equation are the same. Okay, I've got 3 more practice problems for you in red. Notice one of them is an amine, so I am going to pause the video and you are going to try working these. Let's see how you did. So you were doing the problems in red. You should have recognized that that last hydrogen was the labile hydrogen, the one that is acidic. So that is, you're going to leave it as a molecule. In this case, the net ionic equation is the same as the molecular equation. Notice that I used arrows going forwards and backwards because a carboxylic acid is always a weak acid. Our next one, hydrobromic acid. Hydrobromic is one of your strong acids, so you need to use a straight arrow in the forward direction. Hydrobromic acid also dissociates when you put it in water 100%, so the bromide ions are going to cancel out, giving you the net ionic equation of H plus H2O makes the hydronium ion. Our last one is called trimethylamine. That's quite a mouthful. There's a lone pair on that nitrogen, so it can accept a proton. So we're going to form an ammonium type cation. So we have CH33NH plus OH minus. And in this case, the net ionic and the molecular equation are exactly the same. All right, so that concludes writing hydrolysis reactions.